depression of freezing point. Definition of freezing point: the constant temperature at which solid state and its liquid state have same vapor pressure, and these two states of substance coexist in equilibrium. Is called freezing point. Point of liquid. Let me explain it with figure. Suppose H2O is taken in two different phases, in two different chambers. In chamber 1, there is water, liquid H2O, and in chamber 2, ice, solid H2O. Water freezes into ice. H2O liquid freezes to H2O solid, and at the same time solid H2O melts into water. The rate of freezing and rate of melting are equal when vapor pressure over the surface of water, suppose it is P1, and vapor pressure over the surface of ice, suppose it is P2, are also equal. P1 is equal to P2. When P1 is equal to P2, when rate of freezing and rate of melting are equal, at that time the temperature is 0 degrees Celsius. Therefore, freezing point of water is 0 degrees Celsius. So, the freezing point of a liquid is that temperature, characteristic temperature, at which rate of freezing and rate of melting are equal, and vapor pressure over the surface of liquid is equal to vapor pressure over the surface of solid. What happens when a non-volatile solute like sugar is added in liquid? Answer is as when a non-volatile solute is added, the vapor pressure over the surface of liquid decreased. However, the vapor pressure over the surface of solid remains unchanged to bring down the vapor pressure of solid. Temperature is reduced. That means at lower temperature vapor pressure of solid equals to vapor pressure of solution. Therefore, freezing point of solution decreased. Let me produce it by drawing graph. If graph is drawn on y-axis vapor pressure and on x-axis temperature, and this is the highest pressure, 1 atmospheric pressure, vapor pressure of liquid increases upside, temperature increases from left to right. Suppose we have taken pure solvent, then by decreasing the temperature, vapor pressure started decreasing. Vapor pressure started decreasing. Suppose this is the vapor pressure of solid, and at point B, this one is B point, suppose, and this is C point. We are considering solvent only. That means I am considering water. So at B point, here is solid, here it is liquid. At B point, the vapor pressure of solid will be equal to vapor pressure of pure liquid. Once again, at point B, the vapor pressure over the surface of solid and vapor pressure over the surface of liquid are equal. At the same time, the rate of freezing and rate of melting are also equal at point B. So point B is freezing point of pure solvent. Now, as soon as the solute added into solvent, the vapor pressure of liquid drops, and it drops, but the vapor pressure of solid remains same. So to equalize the vapor pressure of liquid, that means solution, equal to vapor pressure of its solid, the temperature is to reduce. That means at point D, the vapor pressure of solution, vapor pressure of liquid solution is equal to vapor pressure of solid. That means at point D, it is freezing point of solution. Once again, at point D, the rate of freezing and rate of melting are equal, and vapor pressure over the surface of solid and vapor pressure over the surface of solution liquid are equal. That's why TF is the temperature freezing point of solution. The difference between the two is depression in freezing point. So I think graph is now clear to everyone. Next point is the depression of freezing point. The depression of freezing point that is delta TF is directly proportional to molality of solution. It means delta TF is directly proportional to M, or delta TF is equal to KF into M, where M is molality of solution if m is equal to 1 mole per kg, then delta TF is equal to KF. What it means? It means the depression of molar depression of freezing point is KF, that is molar depression constant is defined as the depression of freezing point when molality is 1. From above equation 1, we may write delta TF, which is equal to KF into M, and M, as we know, can be written as number of moles of solute by mass of solvent in kg. So it should also be written as mass of solute in gram by molar mass of solute, mass of solvent in gram by 1000. So 1000 will go up, and in this way we have the formula where W1 is mass of solute in gram, M1 is molar mass of solute, W2 mass of solvent in gram, and delta TF, which is equal to TF minus TF naught. So TF is freezing point of solution, and TF naught freezing point of pure solvent. Now the next question is depression of freezing point is a colligative property. Depression of freezing point is a colligative property. But before going into that, let me have Van 't Hoff factor, Van 't Hoff factor, which is expressed as I. The formula delta TF is equal to KF into M. If you are putting I before KF, then I is Van 't Hoff factor, where I is Van 't Hoff's factor. Van 't Hoff factor used in association and dissociation of solute. If take example NaCl dissociates into Na plus Cl minus in solution, then its Van 't Hoff factor in this case will be 2. Take another example, CaCl2 is solute and it dissociates as Ca2 plus 2Cl minus. Then in this case Van 't Hoff factor is 3. However, if a solute neither dissociates nor associate, then value of I is equal to 1. Now let me explain one more question. Explain why depression of freezing point freezing point is a colligative property. Answer is very simple. We know delta TF is directly proportional to M, and delta TF is directly proportional to number of moles of solute by mass of solvent in kilogram. If the mass of solvent in kilogram is constant, then delta TF is directly proportional to number of moles of solute. It means delta TF is dependent on the number of solute particles in solution and not depending on the nature of solute. Therefore, depression of freezing point is a qualitative property. Now I am coming to the topic real life application of depression of freezing point. Depression of freezing point. Real life application of depression of freezing point. First, salt on icy road. Salt on icy road. In fact, when snow falls a lot at the road and vehicle movement is almost ceased at that very time, salt is spread over the road to melt the snow or to melt the ice. This prevents the freezing or lowering freezing point. Prevents freezing by lowering freezing point. Another example is anti-freeze in a car radiator. Ethylene glycol lowers freezing point. Depression of freezing point arises from the same fundamental principle. Addition of solute lowers the vapor pressure of solvent. In our next discussion, we will study the most powerful qualitative property used in chemistry and biology, that is